Hello and welcome to Physics Lecture 5. Today we're going to be covering dimensional analysis in SI units. So first let's start off with the SI unit system. So the SI unit system is, like I said in a previous lecture, I think number 4, it's an extension of the metric system. The SI stands for Système International, International System in French, and it's comprised of 7 base units, which can then be transformed into any number of derived units. So our base units are for distance the meter, for mass the kilogram, for time the second, for electric current the ampere, for temperature the Kelvin, for number of particles the mole, and for, I believe it's luminosity, the candela. And these are abbreviated M, kg, S, uppercase A, uppercase K, MOL, and CD. And notice that all the unit names are lowercase, that is SI convention. So derived units are from any combination of SI units. For example, we have the Newton, the unit of force, which is equal to the kilogram times the meter divided by second squared. We also have the joule, the watt, the Pascal, degree Celsius, and many, many more. And these are all units that we will talk about later in this course. And SI units can also have prefixes which denote like larger or smaller units. So, for example, a kilogram is 1,000 grams, even though the kilogram is the base unit. And so the prefixes that are most commonly used are tera, which is 10 to the 12, giga, which is 10 to the 9, mega, which is 10 to the 6, kilo, which is 10 to the 3, etc. You can read off the slide yourself. And basically, the point of these is to create units whose sizes are more relevant. For example, you wouldn't describe the size of an atom with a meter, or the mass of a skyscraper with kilograms. You describe them with, picometers or teragrams. Or like how big a movie is, a movie file. You wouldn't say it's some number of bytes. You'd say it's gigabytes or terabytes. Well, hopefully not terabytes, but definitely at least gigabytes. And yeah, so when I say 10 to the 12, 10 to the 9, etc., it means that 1 giga something is equal to 10 to the 9 of that something. A gigameter is 10 to the 9 meters, or a billion meters, if you're familiar with this 10 to the number notation that I've talked about earlier when I introduced scientific notation. So let's get into kind of the meat of this lecture, which is dimensional analysis. So the principle behind dimensional analysis is that when we multiply or divide quantities, their units also multiply and divide. When we add quantities with 2 different units, we can't do that, but we can add like 7 meters and 12 meters is 19 meters, right? But we can't add 17 meters and 12 seconds. However, 17 meters times 12 seconds, or using the example on the slide, 10 meters times 10 seconds is 100 seconds times meter. And I wrote it as SM, not MS, because MS is milliseconds. That's 10 to the negative 3 seconds. That means that there's 1,000 milliseconds per second. And 10 meters divided by 10 seconds is, the slide is wrong. It should say 1 meter per second, or 1 second to the negative 1 times meters. That is my bad. But yeah, and notice that meters per second is the units of velocity, and we're doing distance over time. So clearly the distance in time units divide by each other to form the velocity units. And negative 1 is the same as 1 over something to the power of 1. So seconds to the negative 2 would be 1 over seconds squared. Seconds to the negative 3 is 1 over seconds cubed. And again, this is something you should know from your basic algebra class. So there are 2 good uses of dimensional analysis. For one, we can use it to check if our formula is correct. So basically we have to think about, let's say we solved for something, for some quantity, in terms of some other quantities. So what unit is the quantity we're looking for, and what units does our formula give? So I'm going to go back to our example from last lecture with a ball falling through the atmosphere, and we're trying to find its terminal velocity. These are 2 random formulas I've made up. Neither of them are correct, but we're going to try and use dimensional analysis to look at them. So the first formula, this column over here, well, this row, is terminal velocity is equal to the mass of the ball m over rho, the density of air, times the radius of the ball squared. And so I'm using square brackets here to denote the units of a quantity. So the units of the terminal velocity are meters per second. I know that I've used this m here for meters and this m for mass. Please don't let that confuse you. So meters per second is equal to, now this kilogram is coming from the mass. So kilograms over kilogram per meter cubed is the unit of density, times meters squared, which is, if we use our fraction simplification, meters cubed times kilograms over meters squared times kilograms, which is equal to meters, which is not equal to the units of terminal velocity. So clearly this formula is wrong. Now our second formula, we have mass of the ball times the speed of sound, v sub s, over rho, the density of air, times the radius of the ball cubed. And so, again, the units of velocity are meters per second, and then meters per second have to be equal to this kilograms times, this is the meters per second from the speed of sound, over the kilogram per meter cubed from density times the meter cubed from the radius cubed. And so, again, gathering our exponents on the correct sides of the fraction, we get meters to the fourth power times kilograms over meters to the third power times seconds times kilograms, which gives us meters per second, which is the correct unit. So dimensional analysis tells us that this formula is wrong, and it tells us that this formula gives the right units. Notice that it doesn't tell us that it's correct, just that it gives the right units. So let's go into using dimensional analysis to predict something. So basically, given some inputs and some outputs, we can use the units of the inputs to see in which way we need to combine them to find the units of the outputs. So here's our example. Assuming that the terminal velocity of a ball in air depends only on its radius r, the acceleration due to gravity g, and, oh, again the slides are messed up, but it should say the density of air rho. Find a plausible formula for the terminal velocity and ignore multiplicative constants. I will come back to this last bit at the end, the multiplicative constants. So here's our solution. It is rather involved, but I'm going to walk us through. So first row, this is just listing out the units. So the units of terminal velocity are meters per second, or second to the negative first power times meters. The units of radius are meters. The units of the acceleration due to gravity are seconds to the negative second power times meters. And the units of the density of air are kilograms per meter cubed. Now what we do is, we know that we are combining all of these quantities multiplicatively. So we can say, we can guess the form of our solution is going to be that terminal velocity is going to be equal to r to the a power times g to the b power times rho to the c power, where all of these are as yet undetermined real numbers. And that the units of this expression have to be the same as the units of this expression. So now let's work with this units. So we have meters per second is equal to meters to the a power, this is from r to the a, times seconds to the negative 2b power times meters to the b power, this is from the g to the b, times kilograms to the c power times meters to the negative 3c power. This is from rho to the c power over there. And combining like exponents with the same base, we get that seconds to the negative first power times meters has to be equal to meters to the a plus b minus 3c power times seconds to the negative 2b power times kilograms to the c power. And now we can set some of these equal to each other. For example, note that there's an implicit 1 on this side of the equation for the exponent of meters. That means that we can set this exponent equal to this exponent. So a plus b minus 3c is equal to 1. And we can do the same thing for seconds. Negative 2b the exponent on this side, has to be equal to -1, the exponent on this side. So -2b is equal to -1. And note that there's no kilograms on this side. Because anything to the 0th power is 1, we can say that there's an implicit kilograms to the 0th power on this side. That means that c has to be the implicit 0. So now, simplifying, we can sub in c equals 0 here and get a is equal to 1 minus b. We move the b over to this side of the equation. B is equal to 1/2 from this equation here, and a is equal to 1/2 from this equation here. And that means that subbing in a, b, and c from here into this expression, we get that terminal velocity is equal to r to the 1/2 power times g to the 1/2 power times rho to the 0th power, which is equal to the square root of r times g. Notice that raising something to the 1/2 power is the same as the square root. Now, we know that assuming that r, g, and rho are the only quantities v sub t depends on, which is almost certainly not true, we've assumed that. And so we found the kind of way that v sub t has to depend on these quantities. V sub t cannot depend on the density of air, and it is directly proportional to the square root of radius and to the square root of acceleration due to gravity. And again, this is just assuming that r, g, and rho are the only factors influencing v sub t. Now, remember what I said earlier about ignoring multiplicative constants. There's nothing to say that this formula is correct, only that we found a correct dependency to match our assumptions. For all we know, v sub t might be equal to 2 times r sub g. Sorry, 2 times the square root of rg, or 97 pi times the square root of rg. There's no way for us to figure that out. So we can only find the dependencies. For example, let's say that we have a ball and we drop it and we find its terminal velocity to be 100 meters per second. And we take another ball with 4 times the radius. We know that terminal velocity is proportional to the square root of r, so multiplying the radius by 4 multiplies the terminal velocity by 2, meaning our new terminal velocity is 200 meters per second. That's why using dimensional analysis as a predictive tool is very helpful. And again, this is subject to the same thing from last time, the fact that the number of unknowns has to equal the number of equations. So fun fact, while I was formulating this problem here, initially I decided to make terminal velocity dependent on r, g, rho, and the mass of the ball, m. But about halfway through writing up the solution, I realized that, we have 4 unknowns, a, b, c, and d, the exponents of r, g, rho, and m, where m is the mass of the ball. But we can only have 3 equations. The exponent of kilogram on the left side, the exponent of seconds on the left side, and the exponent of meters on the left side. So we'd have 3 equations and 4 unknowns. That means we'd be unable to get a solution. So I had to revise the problem to only make it dependent on 3 quantities. And yeah, again, the reason that we had only 3 equations is because there are only 3 units that we're dealing with: the meter, the second, and the kilogram. So that is something that you have to keep in mind whenever doing a physics problem, not just when you're doing dimensional analysis. But yeah, this is a very helpful tool to have when you want to check if your solution is correct or kind of get an intuitive understanding of what you should be seeing. And yeah, that is all for today. Thank you for watching this lecture.